All right, welcome back, MA 106. This is skill number 8. We're talking about variations still, and we have turned the tables. We did direct variation in skill number 7. So that's the idea of sort of two variables that move in sync with each other, right? You sort of increase one and it increases the other. Pretty naturally, right? The thing that would come next would be what we call inverse variation. Right, so inverse means sort of like flip-flopping something around, sort of turning it upside down or reversing it. And so inverse variation is when you have two different variables, right, two different sort of values that are moving in opposite directions. So that is, as you sort of increase one, the other one drops a certain amount, and vice versa, right? As you sort of drop one, it will increase the other. This, in theory, is sort of just as common as direct variation. We had a bunch of different direct variation examples, and we could come up with many more for inverse variation. Also, it's going to have a little bit of a different setup, which, of course, we'll get into. Let's just talk concepts for a minute here. In the book, right, our sort of example here that we have a little visual for is the relationship between gears, sort of gears that are meshed together. In particular, right, if you look at two different gears that are meshed together and they have different sizes, so different diameters, right, sort of small and large. What happens if they're in sync is the speeds that they're rotating sort of have the opposite relationship. So that is the larger the gear gets, the bigger the diameter, the slower its RPMs are going to be when it's meshed with another gear, right? So that is, or sort of said another way, right? A gear that's spinning faster has to be a gear that's smaller. The diameter has to be smaller. So the RPMs here and the size of the gear, so the diameter and the RPMs, have an inverse relationship. As the diameter goes up, the RPMs go down, and vice versa. If you're going to raise the RPMs, you're going to have to lower the diameter accordingly. Other examples that would sort of have this relationship, something like mass versus acceleration, right? If you're thinking of it in terms of a car, how heavy is your car, right? If you have a truck or something, right, and you're sort of looking at the acceleration when there's nothing in the truck bed versus if you load it up, when in the commercials, you're loading it up with bags of concrete or something, right? 1,000 pounds of concrete in the back, right? As you put more weight on it, your acceleration is going to go down, right? I think conceptually that sort of makes a lot of sense intuitively. The heavier something is, the sort of slower the acceleration is going to be, and vice versa. Similar kind of things if you think of drag on a car versus the sort of miles per gallon, right? What would be sort of the mileage? The more drag that the car has, the lower the miles per gallon, right? If you're trying to sort of get better mileage for your car, you sort of need to make it more aerodynamic, and you need to sort of drop the drag. So if you lower the drag, you're going to get better miles per gallon, and vice versa. I have also found that another sort of inverse relationship would be the number of bad jokes I have in a video versus my overall number of subscribers. If I put more and more bad jokes into my videos, I've found that my subscribers and sort of overall views go down. So that's just a little bit from my life. In any event, so what's actually going on here? What's the kind of setup we're going to use? In the previous section, right, when we were talking about direct variation, we used proportions. What we're going to use here are multiplication pairs. In theory, you could kind of do a proportion style thing, but because the relationships are all flipped around, it's a little bit tricky to try to set them up. So rather than do that and try to have to really think hard about what's going on, we're going to set it up with multiplication pairs. That's pretty scribbled. And so the idea is you're just going to sort of have whatever your two sort of variables are. So in this case, we have kind of like RPMs 1 and diameter 1. If you multiply them together, it should be equal to the values you would get from multiplying the same pair in your second scenario. So you kind of have scenario 1 versus scenario 2, and you're multiplying your values together. In theory, right, what's sort of happening is, you have some kind of constant value that you're sort of always multiplying to, and so the give and take here is, well, if I increase the R value here, I have to drop the diameter here so that I still multiply out to the same value. That's kind of the math concept that's going on. Let's look at a gear one from the book. We'll look at a few different examples, of course, as always. So what do we got? So our first example here, you have a 4-inch gear that's rotating at 120 RPMs. It's meshed with a 9-inch gear. So the question is just how fast is the 9-inch gear going to be turning? What are the RPMs for the bigger gear? So my setup, right, I have my sort of two different pairs. I'm multiplying the RPMs and the diameter together. We don't need to think too hard about like what are the units here. We're doing the same thing on both sides, so we're kind of just ignoring the units, honestly. So this is my setup, right? My small gear versus my big gear. As always, right, I mean, this is sort of resolved. We're trying to solve for the larger gear's RPMs, right? In theory, you could kind of throw your numbers in right off the bat. This is 4 times 120 would be this 9-inch diameter times the missing R. You can do that. This is sort of algebraic. We solved first. That is, we're going to divide by this large diameter to get this sort of missing R value by itself, right? So we're sort of dividing by this 9. And you can see we end up with the same thing here. So 4 times 120 divided by 9. It looks like this one's going to turn out to be 53.3 RPMs. So that's a smaller RPM than we have for the 4-inch gear, and that's the kind of answer we are going to expect, right? As the gear size goes up, as the diameter goes up, the RPMs are going to drop. So that's what we're looking at. These are relatively short, so let's do a couple more. What's our second example here? This is mass and acceleration, right? Try to get this guy positioned right. So a stock car has a mass of 2,200 pounds, right? Sort of 2.2 tons, and accelerates at a rate of 9.3 miles per hour per second. Acceleration, right, is sort of a distance over time squared kind of value. So 9.3 miles per hour per second. So when the mass is 2,200, that's our acceleration. After replacing the stock parts with lighter carbon fiber parts, the car weight has sort of dropped to 1,842 pounds. So we've dropped the weight by sort of almost 400 pounds. So what is the acceleration of the car now that it's lighter? So the relationship, right, is we drop the weight, our acceleration should go up. Should get a higher miles per hour per second. So my setup, again, I'm setting up the multiplication pairs, mass times acceleration for sort of situation 1 versus situation 2. If I started to sub these values in, right, this is 2,200 pounds times 9.3. So that's going to equal 1,842 times my new acceleration, right? So then to get the A, I'm going to do a division. Both of the sides get divided by 1,842. Again, you can kind of do this by throwing the numbers in first, or you can do as the book suggests and sort of do it almost as a formula, right? Get sort of a generic formula, rearrange it, and then you sub everything in. You can see we're ending up with the exact same calculation here in the end. So either approach is fine. Our acceleration, if we sort of crunch all these numbers, is going to end up as 11.1 miles per hour per second. Did the acceleration go up? Yes, it did, right? 9.3 miles per hour versus what? 9.3 versus our new one, which is 11. The weight dropped, the acceleration went up. Right, this is sort of telling us we're on the right track. Let's just do another gear one. Just kind of quick from the exercises, number 5. You can also talk about the gear size in terms of the number of teeth on the gear. So gears, you could do obviously rotations versus diameter or the radius, or you can sort of use the number of teeth as a stand-in for the gear size, right? All those things are related. They would be directly related, I guess, right? The diameter of the gear versus how many teeth are on the gear. That would be sort of a skill 7 problem. When we get the RPMs in the mix, it becomes a skill 8 because it's an inverse relationship. So a 21 tooth gear is rotating at 2,500 RPM. It's meshed with a gear that's rotating at 2,100 RPM. So then the question is, how many teeth does the second gear have? So it's the same kind of relationship. We're just solving for the sort of size rather than the RPMs. So all I'm going to do is I'm going to set up, right? So 21 teeth times 2,500 should equal, right, sort of X many teeth on the second gear times 2,100. Solving for my X, I'm just going to divide by this 2,100. Oh, that's interesting. 21 over 2,100, right? That's actually going to divide and leave us with the 100 on the bottom. So it looks like this is going to be 25 teeth. 21 times 2,500. We'll sort of just do this in order, right? Divide by 2,100. Yeah, 25 teeth. This is one where the numbers from a real world perspective matter, of course, right? Number of teeth on a gear has to really be a whole number or else it doesn't really make sense. So hitting 25 on the nose here is what we're after. So gear 2 is going to have 25 teeth. And that's the setup. I'm going to do a second video that's a little shorter. In theory, you can solve these using a constant, but this sort of multiplication pair stuff also works just fine. So don't feel like you can't just sort of use this multiplication pairs and go from there. All right, so that's it for now. Check in for video 2 for the other solution technique.